Hi everyone, welcome back. Let's see one of the concept called a resource allocation graph. Right? This concept is useful for to cover the concept of deadlock avoidance. That's why before moving for the concept of deadlock avoidance, I have taken this concept. Right? So resource allocation graph, I can also call it as a rack, which is generally used for to represent how the resources are used by processes. We are going to represent in the form of some pictorial representation, right? Which means which can simply define the state of processes, right? So that by looking at the diagram, we can able to define how many processes are there, and how many resources are allocated. We can simply define how many resources are allocated, how many processes are allocated for the resources. Like that you can able to solve various kind of questions. Or if I say how many resources are available, how many resources are available, or we can answer for what are the various kind of future requests, like that we can able to answer many questions by looking at this resource allocation graph, right? And also we can define whether the deadlock will occur or not. We can able to define with the help of this rack, right? So generally guys, what is a graph? Graph means it's a collection of vertices and edges. Simply I can say it's a collection of vertices comma edges. Here in this resource allocation graph, vertices means it's of two types. One will be a process, another will be a kind of a resource, right? So generally process or a kind of vertices I can represent in the form of circle, and resource is a kind of a vertex which can be represented in the form of square shape, right? These kind of things that we have seen earlier itself, right? Now here the resources can be a single instance or it can be a kind of multiple instance, guys. I mean, if the resource, if I am going to represent with one instance, I can call it as single instance resource. Similarly, I can go with the multiple instances. I can represent this as multiple instances. Okay, this is all about the vertices. Coming to the edges, basically edges are going to be represented between the vertices, right? For example, if I say this is a vertex Pi and there is a resource Ri, if the edge is like this, process Pi is using the resource Ri. That is the meaning of it. Or process Pi allocated the resource Ri. This is the meaning of it. Okay. So for example, there is a process Pi and array will be like this. Sorry, I have to go with the resource as some square shape. This is Ri. I have to represent this also a kind of resource. Right now, this means is what? Process Pi request for Ri or process Pi needs the Ri. Right? There is some other symbol is there. Process Pi where dotted arrow will be there for the Ri. The meaning of this one is process Pi is claiming for the resource Ri is belongs to me. Like that we can able to represent, right? So if your graph is collection of all these elements, I can call it as a resource allocation graph. For example, if I try to draw one example, there is a process Pi, or I can go for fixed one P1 and P2. Process P1 is requesting for, observe guys, is requesting for R1. Let's say it as R1, and but actually this was allocated to someone P2, and there is one more resource R2 is there that was already used by the P1, and but it is actually requesting by the P2, right? This is a kind of RAG. I can call this as a single instance graph. Single instance graph. Guys, is there a deadlock here? Just think about it. Yes, deadlock is occurring. The reason is you observed a kind of a loop. P1 is requesting for R1, but it is holding by P2, and P2 is requesting for R2, but it is holding by P1. We can say simply it's kind of a deadlock. It's kind of deadlock, right? Which means that in single instance resources graphs, if there is a cycle, I can definitely say deadlock existed. Okay, fine. Let us try to draw one more RAG. Let us take, there is a resource R1, there is a process P1, process P2, resource R3, one instance of resource R2, one instance of resource R1, two instances of resource R3, and one instance of one process P3, and there will be three instances of resource R4. So out of these three instances of resource of R4, one will be used by P3 already. Now I am trying to implement the graph like this. Requesting like this. This is requesting like this, and which is actually let's say like this. Guys, now tell me, is there any kind of here I can say, is there any kind of deadlock? Before that, let me call this as a multi-instance resource allocation graph. Why means, if you take at least one resource having the more than one instance, that's why I call this multi-instance resource graph. Now tell me, is there any kind of deadlock? Is P1 is blocked or not? P1 is blocked because P1 blocked because P1 is using resource R3. That's good, resource R3, but waiting for resource R1. That's why it is blocked. So P1 is blocked. What about P2? Does P2 is blocked or not? Yes. P2 is using the resource R1 and waiting for R2. That's why it is also blocked, right? So means P2 is using resource R1 as well as R3 and waiting for R2. That's why it is blocked. What about the P3? Does it scheduled? Yes. P3 has got all the resources. That's why it will be scheduled. Right? Yes. Now, is there a deadlock here? Just think about it. There is no deadlock. Because once the P3 is scheduled, it will release all the resources. Then P2 will definitely get the resource and it will complete its execution. Right? Once the P2 completes execution, P1 will be executed. This is a way you can avoid the deadlock. Here the point is, and is for example, if I add one more line like this, does it having deadlock? Yes. P3 also now blocked. The reason is P1 is already blocked and P2 is blocked because of R2, and P3 also blocked because it requires this one, right? Because this resource is already allocated to P2 and this resource is already allocated to P1, and as it is requesting for this one, it will lead to a kind of deadlock, right? Observe how the deadlock will be. It's a kind of like this, right? Yes. So which I can say there is a kind of deadlock. One important point you have to observe, if I say there is a deadlock, definitely there will be a kind of cycle. It can be a cycle, right? But if I say there is a cycle, I cannot guarantee deadlock existed. This is not true in multi-instance graph, not in the single instances, right? In single instances, if there is a cycle, definitely there is a deadlock. If there is a deadlock, definitely there is a cycle. Both are possible. In multi-instance graph, if deadlock existed, cycle will be definitely there. But if cycle is there, deadlock cannot guarantee, right? So for that, if you want, I can give an example. For example, let's say, I can draw. Suppose for example, there is a resource R1, there is a process P1, there is a process P2, and a resource R2. P1 is requesting for resource R1, and for example, two instances are there. P2 is already allocated with resource R1, and R2 having two instances. One instance is already allocated to P1, one instance already allocated to P4. Now P2 is requesting for a resource. For R2. Now observe, guys. If you are able to clearly observe something kind of look, right? Before that, let me say there is a process P3 which is already assigned with some resource. Now observe, here it's a kind of a loop. Right? Even it's a kind of a loop, it doesn't mean that not a deadlock. The reason is what? Simply tell, because once try to observe, once P3 completed its execution, that resource will be given to P1. Then P1 is fully executed, so the loop is terminated. Or if P4 completes execution, that will be given to P2, then also it will be free, right? Yes, this is the way I can say that here when a loop is there will not be any kind of deadlock. That I cannot guarantee, right? When the loop is there might not be a deadlock. That you have to understand. Okay, fine. So the same thing I can represent this in the form of tabular representation, guys. Not only in the form of graphical representation, I can go with the tabular representation like this. So we are having the two process P1 and P2. I am trying to draw the tabular representation for the single instance graph. P1, P2 are there, and this P1, P2 process are using R1, R2. Am I right? Are using R1, R2. That will in terms of like for example, if I say they are allocated, and this is meant for need of R1, R2, right? So for example, does P1 allocated with R1 or not? Try to observe here. P1 is allocated with R1 or requesting for R1? So is it allocated? No. Does P1 allocated with R2? Yes, it is allocated. That's why we made as 1. P2 allocated with R1? Yes, it is allocated with R1. Yes. Now P2 allocated with R2? No, 0. Which means that whenever you are going to get in arrow for the process, I can say it as allocated, and whenever you are going to get out arrow, I can say that I am requesting or need, right? Then P1 is requested for R1 or not? Yes, P1 is requested for R1, so that's why I made it as 1, and for R2 it is not requested, 0. P2 is requesting for R1? No, allocated, so that's why 0. P2 is requesting for R2. Like this I can able to represent the table representation for the respective single instance graph. Let's say it as G1. Now for G2, can we draw it? Yes, you can draw it by yourself so that you can get the clear understanding. Now let us try to draw for the table representation for the graph G3. right? How many processes are there here? P1, P2, P3 and P4. And how many resources are there? R1 and R2 resources are there. I am trying to define for allocation. Later I am trying to define it for requested or needed of R1 and R2, which is very simple. By looking at the diagram we can draw. Does P1 is allocated with R1? Allocated with R1? No, not allocated with R1. It is just simply requesting it. Requesting it means what? At the R1 I am making it as 1. And what are the out arrows? Or else you can go with like this. To go with the P1. What are outgoing arrows? That will be defined by need. And what are the incoming arrows? That will be defined by the allocated, right? What are the incoming arrows for P1? R2. I will make it as 1. Good. Next for P2. What are the incoming edges? Incoming edges is R1, means allocated. What are the outgoing edges? Requesting, means R2. Similarly, for P3, what are the incoming edges? Incoming edges is R1. What are the outgoing edges? Nothing. And for P4, what are the incoming edges? R2. What are the outgoing edges? Nothing. So I can fill the remaining things as 0. This is the corresponding table representation for the corresponding RAG graph. Right? Yes. So the reason why I made them mention in the form of a table is which will be used for to simplify our task, where you can apply the banker's algorithm. That we will see in the next video. Hope you understood this video clearly. Thank you.